In this video, we're going to take a look at an introduction to probability generating functions. Now, a probability generating function, often just shortened to PGF here, is a mathematical function that stores the details of a probability distribution. Now, it does this in quite a unique way, and the way that it does this is in the form of a polynomial. And we'll see that in a little bit more detail later on in this video. Now, probability generating functions only apply to discrete probability distributions such as the Poisson distribution and the binomial distribution. So for that reason then, you will not see anything to do with the normal distribution within this chapter here on probability generating functions. Now let's say we have a discrete random variable, let's call that x here, which has the following probability mass function, okay? Then the probability generating function here of our discrete random variable x, this is given as follows. Now on the surface here, I don't think this result is particularly intuitive. So let me just try and briefly explain this here. So the g just represents a probability generating function. The subscript here represents the discrete random variable. So in this case, because we have the discrete random variable x, our subscript is x. If we had the discrete random variable y, this would be g of y, okay? And then the t here, this just represents a dummy variable. So this here is the probability generating function for x in terms of t, where the t here is just a dummy variable. So it doesn't actually represent anything, we just use it to represent our polynomial, okay? Now this is equal then to the summation here of the probability of our discrete random variable x being equal to some value x, and then we times that by t to the power of x, where again this t here is just a dummy variable. So as we mentioned then, t here is just a dummy variable. So to help illustrate this concept then, let's look at a basic example. Now, let's say that we're given the random variable x here, which has the following probability distribution. Okay, so it's in the form of this table here. So the top row, x, this is the values that our random variable x can take. So we've got 0, 1, 2, and 3. And then underneath here, we have the respective probabilities. So we've got 0.1, 0.3, 0.4, and then finally 0.2 here. Well, in that case then, the probability generating function of our random variable x then, this is given as follows. So we've got g of x here in terms of t. Now, the g, don't forget, this just represents a probability generating function. The subscript here, this x, well, this just represents our random variable x. If this was y, for example, so the random variable y, this would be g of y in terms of t. And then don't forget here, we mentioned it on the previous page, the t here, this is just a dummy variable. It's nothing special, we just use it to represent our polynomial, as you can see here. Okay. Now, hopefully, you might notice straight away that the coefficients of t are these probabilities here. So 0.1, 0.1, 0.3, 0.3, so on and so on. Okay. Now, when t equals 1, the terms of the probability generating function sum to 1, since the summation then of the probabilities here is equal to 1. And this fact here shouldn't be new to you. We established this in chapter 1 on discrete random variables. Okay, so this here is a really important property basically for probability generating functions, as you can see here. Okay, so let's summarize then. So for any probability generating function, g of x at 1 is equal to 1. So that's what we just mentioned here. So when t is equal to 1, the terms of the probability generating function sum to 1. Okay, so that's really important. Do make a note of this here. Okay, and then finally here, the probability generating function of a discrete random variable x, so g of x at t is equal to the expectation of t to the power of x. Okay, again, really important here. Do make a note of this. This is how you will see it in the formula book. Okay, I must say here that probability generating functions is potentially one of the trickier topics within Further Stats 1. However, I personally think it's one of the more enjoyable topics within Further Stats 1. It's a little bit abstract compared to maybe some of the other topics, such as hypothesis testing, stuff like that. But like I said, it is personally quite an enjoyable topic. So I am hoping, maybe not necessarily by the end of this video, but by the end of this chapter, you will start to appreciate probability generating functions and their applications. Okay, it is worth saying that differentiation will also come up within this chapter here on probability generating functions. So before we kind of carry on here and we get through the next couple of videos, just go back and make sure that your year 2 A-level maths differentiation is up to scratch. If it's not, you might find some of the later parts of this chapter a little bit more challenging. Okay, so that gives us everything that we need then for our introduction here to probability generating functions. Let's just take a look then at some practice questions. Let's get started here then with question 1. Now for question 1, it just asks us to denote the probability generating functions for the following probability distributions. And as we can see for this question here, we've got two probability distributions, one in part A and one in part B, both of which are in the form of a table. So let's begin then with part A here. So for part A then, we've got this probability distribution given here, and we're working with the random variable x then. So for the PGF here, this will be g of x. So g of x here in terms of t. So this is equal then to some polynomial. So how do we derive the polynomial here then? Well, for the coefficients, they're given by the probabilities here. So we've got 0.4 to begin with. And then we times this by t to the power of x. So if x is equal to 2, we get 0.4 t squared. Nice and straightforward. That gives me my first term. Okay, so let's keep going here. Now for the next one then, it's going to be 0.5 as the coefficient. So plus 0.5. We then have t here to the power of x, where in this case, x equals 4. So we get 0.5 t to the power of 4. And then finally, for the very last term here, we get 0.1. So plus 0.1 t to the power of 6 there. Okay, and there we have it. So nice and straightforward. That gives us the solution there to part A. Now let's move on to part B then. So for part B then, now we're finding the PGF for this probability distribution given here. So we're now working with the random variable y here. So this is now going to be g of y in terms of t. So g of y in terms of t then. So again, just using the same method that we saw for part A, we're going to get 0.2 t to the power 1 to begin with. So we get 0.2 t to the power 1 then. So that's my first term. Let's keep going here. So we now get 0.15 t to the power of 2, or 0.15 t squared. 0.15 t squared there. Keep going here. So 0.4 t cubed. 0.4 t cubed. And then finally here for the very last term, we get 0.25. So plus 0.25 t to the power of 4. Okay. And there we have it. So hopefully nice and straightforward. That gives us the solution then to question 1. Moving on to question 2 then, where we have the discrete random variable x, which has the following PGF here. So we've got g of x in terms of t, and that is equal then to this polynomial here. Now for question 2 then, it's asking for us to find 3 probabilities. So let's begin then with part A. So for part A then, we're looking for the probability that our random variable x here is equal to 0. Okay. Now there's two ways to do this really. The first way would be to use the fact that we can express this PGF here in the form of a probability distribution. Okay. So if we express that probability distribution as a table, finding probabilities is nice and straightforward. The other way to find these probabilities here, so for A, B, and C, would be to use the fact that the coefficients here correspond to probabilities. Okay, and that's the method that I'm going to use here for this question. So for the probability that x equals 0 then, that's when little x equals 0. Okay, so what that means then is we have t to the power of 0. That's when t is to the power of 0. Now in that case then, that would correspond to this term here, okay, because t to the power of 0 is 1. So what I've got here then is 0.1 t to the power of 0, okay? So in that case then, this probability here corresponds to the 0.1. Okay, and there we have it. So that's the solution to part A, hopefully nice and straightforward. Now for part B then, what we're looking for here is the probability that our random variable x here is less than or equal to 2. So this is the same then, or this is equal to the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability then that x is equal to 2. Now we already know this probability here. We established that in part A, so that's 0.1. So then for the probability that x equals 1, well, that's for t to the power 1. So that's this term here then. And then the coefficient here gives us the probability. So that's 0.25. And in that case then, for the probability that x equals 2, that corresponds to this term here and this coefficient. So that's going to be 0.35. Okay. So 0.1 plus 0.25, that gives me 0.35. So 0.35 plus 0.35, we get 0.7 there. Okay. And there we have it. So that's the solution to part B. And then finally here for part C, we're looking for the probability then that x is between 2 and 3 inclusive. So 2 and 3 inclusive, like so. Well, this is the same then as the probability that x equals 2 plus the probability then that x equals 3. Okay. Well, we already know this probability here. That's 0.35. So 0.35. Then for this probability here, that corresponds to this term and the respective coefficient of 0.3. So 0.35 plus 0.3, that gives us 0.65 there. Okay. And there we have it. So that gives us the solution there to question 2. Moving on then to the very last question here, question 3, where we have the PGF of a discrete random variable x, which is given as follows. So we've got g of x here in terms of t, and that is equal then to k times 1 plus 3t plus t squared all squared. And for the first part of this question, then part A, what I want to do here is find the value of k. So for part A then, and to answer part A, we need to use an important property here of probability generating functions. So we're going to use then the fact that g of x at 1 is equal to 1. Okay. So in that case then, what we have here is k times 1 plus 3 lots of 1. So 3 lots of 1 plus 1 squared, which is just 1. That's all squared, and that is equal then to 1. Okay, so if we simplify this here, then we get k. So I've got 1 plus 3 lots of 1, so that's going to be 1 plus 3, which is 4, plus another 1, so that's 5. So if we square that, then we get 25. So I've got k times 25 here. So in other words, what I've just got then is 25k, and that is equal to 1. So in that case then, if we want the value of k here, all I need to do is divide both sides by 25. And in that case then, we find that k is equal to 1 over 25. Okay, so there we have it. So that's the solution to part A. Now for part B then, it asks us to write down the probability distribution of x. So where do we begin here for part B? Well, for the probability distribution of x then, what we need to basically do here is expand this bracket. So I've got 1 plus 3t plus t squared all squared. Okay, so let's just start by expanding that then. I've got 1 plus 3t plus t squared, and this here is squared. Okay, so it's up to you whether you write as a product here or you just expand it. It's completely up to you, but either way, what you should get then is 1 plus 6t here plus 11t squared plus 6t cubed, and then finally plus t to the power of 4. Okay, so I can see here then the values of x that we can take for our random variable x. So in that case then the values that we take here are 0, 1, 2, 3, and 4. I've got 0, 1, 2, 3, and 4 there. Okay. So that's for x there, little x. These are the values that our random variable x can take. And then the row underneath it, we have the probabilities. Like so. Now remember, these correspond to the coefficients here. Okay, so in that case, to find the coefficients, we now need to times this here by 1 over 25, by k in other words. Okay, so what I get then is 1 over 25 times by this here. So I've got 1 plus 6t plus 11t squared plus 6t cubed. And then finally plus t to the power of 4. Okay, so what I get then is 1 over 25 times 1. So I get 1 over 25 there for my probability. Now when x is 1, so that corresponds to this 6t here, we get 6t times 1 over 25. So I get 6t over 25. So the coefficient then is 6 over 25. So like you can see here, nothing challenging. So for the next one then we get 11 over 25. Keep going here, 6t cubed, we then times it by 1 over 25, so I get 6 over 25 again. And then finally we've got t to the power of 4 here times 1 over 25. So again, I get 1 over 25 there. Okay, and there we have it. So nice and straightforward. That gives us the solution to part B. And that gives us the solution there to the very last question, question 3. And that actually brings us to the end of this video on an introduction to probability generating functions.